Technology. Professor Vijay P. Singh is a distinct professor, Texas A&M University, USA, as an expert, and he is the alumni of College of Technology. I welcome Dr. Alnanda Ashok. She is the Dean of College of Technology, and all the registered participants from national and international era to this first international webinar series of College of Technology by Professor Vijay P. Singh, with topic entitled on Entropy Theory and its application in Hydrologic Engineering. And as Professor Shivaprasad told, one more webinar, I am presenting a very brief CV of Professor Vijay P. Singh. Professor Vijay P. Singh is a distinct professor and Carolyn and William and Lehrer Distinguished Chair in Water Engineering, Department of Biological and Agricultural Engineering, Department of Civil Engineering, Texas A&M University, College Station, Texas, USA. His research interests include surface water, hydrology, groundwater hydrology, hydraulics, irrigation engineering, environmental quality, and water resource and hydrologic impact of climate change. His professional heights includes 1,286 papers published in referred journals, 330 conference papers, 30 books, 72 edited books, 115 book chapters, and 72 technical reports and special issues of journals. He is the editor of many international journals. He has been awarded during the year 2012 Texas A&M University Bush Excellence Award for Faculty in International Research and University Distinguished Professor Award during the 2019 and Lifetime Achievement Award, Environment and Water Resource Institute, American Society of Civil Engineers. He is a fellow of EWRI, AWRA, IWRS, IASWC, IAH, and IE, and a member of 11 international science and engineering academics. He has received 92 national and international awards, including Normal Medal, Crystal Rock Award, Joe Award, Anchor Award, and also he received 3 honorary doctorates. He has served as a president of American Institute of Hydrology, chair of Watershed Council of American Society of Civil Engineers, and is currently president of American Academy of Water Resource Engineers. For 4 lifetime achievement awards, including College of Technology and Pantanagar, University of Pantanagar. I welcome you all once again for this international first series of international webinar of College of Technology. Thank you, sir.
Thank you, Professor Jyoti Prasad. Now, I request our Dean College of Technology, Professor Alnanda Ashok, for her introductory remarks and also to say something about our College of Technology. Thank you.
Thank you, Dr. Prasad. I am delighted, rather after listening the achievements of Professor Vijay P. Kumar. I am really honored to have Professor Vijay P. Singh with us. I welcome you, sir, and I would like to tell all the participants that soon our Vice Chancellor, Professor Tej Pratap, he will also join us because right now he is busy with the meeting, so he will join us after a few minutes. So by that time, I welcome Dr. Professor Vijay P. Singh, and I heartily welcome to the international webinar on entropy theory and its application in hydrology engineering. I take this opportunity to say a few words about our College of Technology. The College of Technology came into existence in this prestigious Pantnagar University in year 1966. The College of Agriculture Engineering was merged with College of Technology. College of Technology has 11 departments offering 8 BTech degree programs, namely Agriculture Engineering, Civil Engineering, Computer Engineering, Electrical Engineering, Electronics and Communication Engineering, Information Technology, Mechanical Engineering, and Industrial and Production Engineering. In addition to it, the college offers 24 postgraduate programs, including a self-financed MCA program. The College of Technology is an ISO 9001-2000 certified institute. Is privileged to have a well-qualified and experienced faculty with judicious mix of creative, talented, and committed academicians. A large number of faculty members hold PhD degree in their respective fields from nation and international institutes of repute. The vision of College of Technology is to become an internationally recognized leader in the field of technical education, research, and extension. All the programs of study are approved by the AICT and accredited by the National Boards of Accreditation. Admissions to BTech program are through JEE, Joint Entrance Examination. Admission to MTech programs are through GATE score, while the MCA programs are through NIM SET score. The college is the lead institute in Uttarakhand in the World Bank project for Technical Education Quality Improvement Program Phase 1, Phase 2, as well as in Phase 3, and is also a regional academy center of CISCO, including CISCO Networking Lab. The college is proud of its infrastructure facilities befitted to modern technological needs. Professor VP Singh, an alma mater of this college. We are so proud of you, Professor VP Singh, that you are our alma mater. And we are really proud that we are welcoming you from your institute for this lecture. Who has been awarded Lifetime Achievement of this College of Technology as well as from the Nagar University. You are welcome, Professor VP Singh. International webinar on entropy theory and its application in hydrologic engineering will be delivered by an eminent personality, distinguished Professor Vijay Singh, an international expert who has grown in knowledge to the greatest height. I welcome him to the first international webinar series of College of Technology. Welcome, sir. This entropy theory has vast applications in view of being Uttarakhand state is rich in water resources, in particular, and in India in general. Hence, the topic chosen by Professor Singh is quite relevant to the scientific and research community working on the water. Once again, I welcome all the national and international participants who are working in the field of water on behalf of entire College of Technology and on my personal capacity to this prestigious webinar. Now, I will not take much time, and I would request our convener to start with Professor Vijay P. Singh expertise, and I again welcome all the national and international participants. Thank you so much.
Thank you, madam, for your brief remarks about our College of Technology. And once again, I am welcoming you for this webinar on entropy theory and applications. Now, without wasting much of the time, I request Professor Vijay P. Singh, distinguished professor, to start his webinar or expert lecture on entropy theory and its application in hydrologic engineering. Professor Singh, please.
Okay. Thank you, Dr. Prasad. But first of all, let me digress a little bit. I would like to express my deep appreciation to Dean Dr. Alaknanda Ashok and Dr. Jyoti Prasad for making very gracious remarks. I'm equally proud to have graduated from Pantnagar, and Pantnagar clearly occupies a very special place in my heart. I've been very fortunate to have had the opportunity to visit Pantnagar many times since I graduated, and I look forward to visiting again. So the seminar topic that I have chosen essentially is a short prelude to the GAN course that I was scheduled to offer 2 years ago. Unfortunately, because of one reason or another, recently because of coronavirus pandemic, I simply could not visit Pantnagar to deliver the course. But hopefully, if circumstances permit, in the very near future, I may be able to come to Pantnagar to offer the course. So let me extend my very warm greetings to all the participants, to all my colleagues and friends at Pantnagar. Fortunately, I still have a number of friends and colleagues working at the university as well as outside the university. So I'm very, very pleased that Dr. Jyoti Prasad asked me to give this seminar. I personally would like to have the seminar more of a discussion. So if anybody has any question anytime during the period of my delivery, please interrupt me and raise a question, because it's a webinar. So I will try to. I have purposely and deliberately attempted to make the seminar as qualitative and as descriptive as I could possibly make it. Now, occasionally you will see some equations, so you don't need to worry about those equations. I'll try to explain to you in very simple language as to what those equations really mean and how we can apply this entropy theory in our daily lives, even outside of hydrologic engineering, even in social sciences. So anybody who has any interest in any area, hopefully should be able to get something out of what I will be presenting this morning or this evening on your end in India. So, but before I start, Prasad, can you hear me well? Can you hear me?
Yes, sir. Yes, sir.
Yes,
Okay.
we can hear you.
Okay, so let me start. First, let's look at the grand challenges of the 21st century. Now, of course, all of us know, and even those of us who are outside of engineering should also know that our grand challenges are basically related to food security, water security, energy security, health security, climate security, environmental security, ecosystem sustainability, and then of course, water, energy, food, environmental nexus. And in a sense, the challenge actually pertains to the survival of humanity, because this seems to be at risk unless we can ensure these securities that I have just mentioned. Now, clearly, in order to ensure those securities, we have to plan, design, operate, and manage water resources systems. And the reason is very simple. If there is no water, there is no security of any kind. It's as simple as that. And then, of course, those of us who are from India remember, the 5 elements that make up our life. And let me recite: Adijal Gagan, Pavan Samira, Panch Tattvaya Adham Samira. So there also I think the role of water has been emphasized as long ago as many thousand years. Now for planning, designing, operating, and managing these water resources systems, uh, the question arises what these systems are. The systems obviously are needed for drainage, flood control, irrigation, water supply, hydropower, river training, navigation, recreation, and a whole host of other purposes. So the water resources systems are also named after these purposes. Now, there are some key questions. Now, of course, for doing any of these activities that I just mentioned with regard to water resources systems, there are some key hydrologic questions that we have to answer. For example, what is the peak discharge if a rainfall event is given? And how often does this discharge of a given magnitude occur? And of course, the next question is, what is the volume of discharge resulting from a rainfall event, and how is it distributed in time? And how much and at what rate does rainwater infiltrate into the ground? And how is the infiltrated water distributed into the Vado zone? And what are the space-time characteristics of droughts? What should be the space-time monitoring of hydrologic data? And what is the rate of groundwater depletion? And what is the rate of groundwater recharge? What is the velocity distribution and open channel flow? And what is the concentration of sediment in open channel flow? And what is the sediment discharge of a river? What is the pollutant discharge of a river? What is the optimal design of a canal? What is the reliability of a water supply system? So these are some of the questions that arise when we plan, design, develop and operate water resources systems. These are the questions that have to be answered. Now, of course, that is where the hydrology comes in the picture. Hydraulics and hydrology, particularly hydrology, being a geophysical science, but also being an engineering science. And the application of hydrology is made through rainfall runoff modeling. For example, this is needed for watershed management, drainage design, pavement design, and so on. Likewise, for flow frequency analysis, which is needed in dam and reservoir design, irrigation management, environmental management. Here I'm just pointing out some key points. There is no time for providing an exhaustive list of where and how hydrology is applied. Likewise, for velocity distribution, which is needed for flow modeling, scour modeling, for modeling bed profiles. Likewise, we need sediment concentration and sediment discharge, which is needed for environmental pollution, bed forms, and sedimentation. Similarly, we need hydraulic geometry for river training works, for river restoration, and we need optimal canal design for irrigation, for drainage, water distribution system design. So we need for designing a water supply system, as well as for computing the reliability of any water distribution system. Now for all of this, in hydrology, if we look at the landscape of hydrologic modeling, we find that there are 4 types of methods for solving the questions that I raised. Of course, the first method is empirical. Empirical by definition means it is strictly based on data. Second, of course, is information theoretic, which is what I will be emphasizing here. And the third one is probabilistic and stochastic, and fourth one is physically based. Now, often when we teach courses, we emphasize these methods, but sometimes we emphasize as if there is no connection among these methods. And my thesis here is that they are all interrelated and they complement each other. They are not substitute for one another. You can learn, excuse me, you can learn a great deal for building physically based models from empirical models. Likewise, information theoretic and probabilistic and stochastic models are also interrelated to each other, and also information theoretic and physically based models are also interrelated. And I'll try to point some of these issues during the discussion here. So let's now get down to the main theme, which is the development of a unifying theory. And by definition, unifying theory means that a lot of seemingly disparate concepts can be brought together under one umbrella, under one roof, so to speak. And entropy is one of those theories, is one of those concepts that I strongly believe should become a subject matter in every undergraduate as well as graduate engineering curricula. Everybody should learn what really entropy is and what the entropy theory is. It does not matter whether the course is undergraduate course or a postgraduate course, or in the US we call graduate course. It should become an integral part of our curriculum. And I'll explain to you, you will get an idea as to why I'm saying what I'm saying. So let's first understand what really entropy is. Now, of course, anybody who has taken a course in thermodynamics, I do remember when I took my course in thermodynamics in second year at Nagar, I learned a little bit about entropy, but there the concept of entropy was taught in a very different manner, in a thermodynamic sense. Here I will emphasize the information theoretic uh, form or information theoretic way, but the two concepts are interrelated. They are not divorced from one another. So in the context of information theory, entropy is really nothing but a measure of disorder, or a measure of chaos, or a measure of uncertainty, or a measure of surprise. And all of these are nothing but different forms of information. And I will explain to you how these different concepts are interrelated, or nothing but the same shades or the same sides of the coin. Just like you have a coin, it does not matter whether you see the coin from the tail side or from the head side. The coin is coin and its value remains the same. Likewise, entropy is also a measure of all these concepts which look different, but they really are not different. For example, if we have more information, that means about any system, that means we understand the system better and we reduce the uncertainty associated with the system. So which means the information and uncertainty are related to each other. More information means less uncertainty. More uncertainty means less information. The whole purpose of collecting data is basically to gather information. We don't collect the data simply for collecting the data or collecting a bunch of numbers. Our purpose is to gather information. That's the reason we do data analysis. And these days, there is a lot of emphasis on data science, basically, which is really nothing but the manipulation, the processing, and the extraction of information from the data. So let me summarize. More information means less uncertainty. And it is the uncertainty that increases the need for information, because more uncertainty means more information is needed. Likewise, it is directly related to the concept of surprise. So in order to explain the surprise, let's assume that there is a random variable. And let me point out right at the outset, if anything is uncertain, that means it is associated with some degree of randomness or some concept of probability. So let's assume that there is a random variable that we can call as capital X, and its particular value is small xi. I is any index which can take value from 0 to 1 to whatever, any number. And P associated with xi is the probability that the random variable capital X takes on the value of small xi. So if the probability is, let's say, of the value xi is 0, that means, there is actually no surprise about the occurrence of x being equal to xi, because there is no probability of the probability occurrence means it does not occur. So if we know for certain that the probability of occurrence of xi is 0, that means there is no uncertainty associated with it. On the other hand, if it is also 1, the probability is 1, that means we know for certain that it occurs. So that means there is no uncertainty associated. We already know what the outcome is. So if the knowledge is there about the outcome and the knowledge is perfect, there is no uncertainty period. And so there is no surprise if the value occurs or this value is associated with the event, that means the event is occurring. On the other hand, let's assume that the probability of the occurrence of this value xi or the event is very low, let's say 0.01. In other words, there is a 1 out of 100 chance that this value occurs. And if this value does indeed occur, then what do we say? Oh, we are very surprised because we did not expect this event to occur, but it does occur. And this is what happens when extreme hydrologic events occur. So that's the reason we design large water sources projects for very large events. Dams are normally large dams, depending upon the size, are designed based on essentially this probability of occurrence for the peak discharge. If you are designing, let's say, nuclear power plant where the risk of failure can be so high that it can cause a lot of damage. So they are designed for very, very large events, which means their probability of occurrence is extremely low, like 1 in 10,000 years. So let me now summarize. So the information content of observing the event xi or the value xi or the anticipatory uncertainty of xi prior to the observation, one can say is a decreasing function of the probability of xi. So the information is gained only if there is uncertainty about the event. Because if there is no uncertainty about the event, you don't gain any information. This is exactly what happens when the networks are not properly designed. You collect a lot of numbers, but those numbers may not really mean a whole lot. You don't need to collect the numbers or the data for the sake of collecting them. They have to provide new information. Otherwise, there is no sense collecting the data. And that's the reason we need to design the networks in a manner that they provide the information that we need. This is exactly what we need to do when we design experiments in the laboratory. So the uncertainties suggest that the event may take on different values. That's the reason the values are a representation of uncertainty. The value that occurs with a higher probability conveys less information and vice versa. In 1948, an electrical engineer come mathematician argued that entropy is nothing but the expected value of the probabilities of alternative values that an event can take on. And so this is what distinguishes entropy from information. Information is uh, a significance of a particular value. On the other hand, entropy, the way it is defined is nothing but the expected value of the expected value of all these information contents or the probabilities of these alternative events. And let me now, okay, so let me go further and then I'll relate to how it is related to the student performance. So the information gained is indirectly measured as the amount of reduction of uncertainty or of entropy. Now let's take the case of a student grade point average. So what does the grade point average mean? The grade point average is nothing but the entropy measure of a student's performance in all the courses that the student has taken. So basically, what do? We basically nothing but average all the grades a student achieves in a particular course, but the averaging is done in a weighted sense because there are some courses that may be only 2 credit hours, some may be 4 credit hours, some may be 5 credit hours, some may be 3 credit hours. So what do is we take an average. This is exactly what we do in the case of entropy. So we take a weighted average, and I'll explain to you a little bit later how this weighting average is done. So given this short prelude or introduction, we find that the entropy has been used and interpreted in different areas. So I just explained entropy as a measure of uncertainty, as a measure of information, but this is also used as a measure of randomness. It is used as a measure of unbiasedness or objectivity, measure of equality. If you are working in social sciences, there is a lot of discussion over there in terms of equality and inequality. And of course, in our country, particularly in India, there's a lot of, there is a lot of political connotation associated with the term equality and diversity. Likewise, it is also used as a measure of lack of concentration, particularly in the area of ecology, where they deal with the diversity of species or concentration of species. In manufacturing or in production engineering, it is also used as a measure of flexibility. And of course, as I explained, it's used as a measure of surprise, measure of complexity. Again, in industrial engineering, it is used, or in mechanical system. Likewise, it can also be used as a measure of departure from the uniform distribution in statistical sciences, or it is used as a measure of interdependence or dependence, or in statistics, likewise, a measure of interactivity or a measure of similarity. I mean, these are the different interpretations of entropy, but basically these are nothing but the different shades of the same concept, which is entropy. So but entropy has been defined in different ways. I just said to you about one concept of entropy that Shannon in 1948 developed, and he developed the whole theory, which is what I will be discussing here, which is called the Shannon entropy theory, or theory of information, or information theory, whatever. Now, entropy actually is defined in 2 domains, a real domain and in frequency domain. In real domain, there are different types of entropy, and depending upon who developed these entropies have been named thereafter. So Shannon developed entropy theory, so it is called a Shannon entropy. In a physicist who I know from Brazil, originally he's from Greece, but Professor Salas, he developed another theory which is very powerful and used in quantum mechanics, in particularly in theoretical physics, which is called now Salas entropy. And I personally use both entropies, Shannon and Salas. And then, of course, there is another entropy called exponential entropy. It was developed at Indian Statistical Institute in Calcutta. And there is a Kapoor entropy that was developed at IIT Kanpur by Professor J.N. Kapoor. And then, of course, there is another entropy called Renyi entropy. Renyi was a Hungarian mathematician. And of course, another very powerful concept as cross or relative entropy called Kullback-Leibler entropy. These are two American statisticians. And there are other kinds of entropies that have been developed, but really these are not very, or they have not been found to be very useful. The two entropies that are most useful are Shannon entropy and Salas entropy. Renyi entropy is also quite useful, but really not as useful, partly because its mathematical form is a little too difficult to deal with in many different cases. So that is why we normally use Shannon entropy or Salas entropy. And even Salas entropy is a little bit difficult to deal with. It is Shannon entropy which is most versatile, and it satisfies a lot of properties that we learn in our undergraduate engineering classes. But these are the different types of entropy in real domain. Real domain means in space and time. But there are also other entropies which are extremely useful, and they are defined in the frequency domain. And there are three entropies. Berg entropy, because Berg did a PhD dissertation at Stanford University. He was a geologist, but he did a tremendous job in developing the Berg entropy. And I'll relate these frequency domain related entropies to the real domain related entropies. And then there is another configurational entropy and relative entropy. Berg entropy is very similar to Shannon entropy. Configurational entropy is also very similar to Shannon entropy, and relative entropy is really not very similar to Kullback-Leibler or cross or relative entropy in the frequency domain. So they are related to each other. In frequency domain, these entropies are used for forecasting purposes. For example, one can construct spectrum using these entropies and then use the spectral analysis exactly the same way that we use in time series analysis for forecasting, modeling purposes. Okay, so let's now focus on the Shannon entropy theory, and we will simply call entropy theory. Now, this entropy theory essentially has four aspects. One, of course, is the definition of entropy. The second one is principle of maximum entropy. And the third element is principle of minimum cross entropy, which is Kullback-Leibler entropy. And then, of course, the fourth is the theorem of concentration. And by the way, I have asked Jyoti to share my PowerPoint with any participant. So you don't need to make any notes, just focus on listening to me. And as I said, if you have any questions, just interrupt me. So now let's, so these four elements are the building blocks. And so the first one is the principle of maximum entropy, and then we will, and the second one is Kullback-Leibler entropy. So let's first discuss Kullback-Leibler principle or entropy, and then we'll come back to the maximum entropy principle. So what, as the name suggests, it's a relative entropy or cross entropy. So why do we use the term cross entropy? It will be clear in a minute. Let's consider a probability distribution Q, which consists of Q1, Q2, Kn probabilities of random variable X, which takes on n value. Now our objective is to derive the distribution of X, random variable X, and this distribution that we want to derive is, let's say, P, which consists of probabilities P1, P2, Pn, and because we have n value. So the objective is to minimize the distance between the distribution that we want to derive and the distribution that is already assumed or is given based on our prior knowledge. So the closer both P and Q are, the greater will be the uncertainty. So we would like to then the principle of maximum cross entropy then is expressed as the distance. D is the distance, which is a function of P and Q, is really nothing but the summation of Pi log of Pi divided by Qi. In other words, we are taking, see, log Pi Qi is nothing but in the logarithmic domain, it is nothing but basically the difference between the two probabilities or two probability distributions, because log of Pi minus log of Qi, and then it is being taken as a weighted average. So here the weighting is specified Pi, because our objective now is to determine the Pi. So if let's assume that there is no prior distribution available in the form of constraint, so we can always assume that the prior distribution is uniform. And uniform means every value is equally probable, which means the Qi is nothing but 1 over capital N, which is the number of values that we have. Then we immediately find the distance is really nothing but log of N minus capital H. Capital H is nothing but the Shannon entropy. So basically, if you take, so that means if we maximize the Shannon entropy or we maximize D, which is Kullback-Leibler entropy, it is one and the same thing. So which means that the Kullback-Leibler entropy is a more general case and includes the Shannon entropy as a special case. And so our objective here is to minimize the cross entropy. And this actually is consistent with the Bayes theorem. And one can actually show that asymptotically, the minimization of Kullback-Leibler entropy or cross entropy is really asymptotically, it results from Bayes theorem. So that means the principle of maximum cross entropy has two major concepts. One, prior probability distribution, and two, measure of distance. And so essentially, one is related to the system to be characterized, which is assumed to be unknown, and the other one is related to the model chosen to describe the system. So the models to characterize the system means we need to specify a set of movements, for example, mean or any other systematic part of the covariance metric. So which means the principle of maximum cross entropy measure can be obtained by minimizing the discrimination information with respect to the given prior distribution over all probabilistic distributions of the system which occur with the given constraint. And that's really what the concept is. So let me explain it in simple terms. Don't worry about these mathematical properties. Okay, what really we are saying is, let's assume that we know something about a given system. And why do we know something about? Because that's the whole purpose of coming to college, because we would like to learn something about the system. So when we try to model the system, we want to make sure that what we know about the system must be preserved, because that is based on facts, that is based on theory, that is based on observation. So when we try to model the system based on entropy theory, we want to make sure that our model is able to mimic the characteristics of the system that we already know. That is the reason we want to minimize the distance between the two distributions. Okay, so let's now move on to Shannon entropy. As I said, the same thing before. The Shannon entropy can be defined as a function, a weighted function of the probability. So H, capital H, is really nothing but the summation of pi log pi. So we don't have any qi anymore here. Now the reason we are putting minus is because log of pi is negative, because probability is between 0 and 1. So its logarithmic would be negative, and we want to get a positive value of entropy, because negative information or negative uncertainty or negative probability won't mean anything. So that's the reason we are putting minus sign here. Now it turns out that this Shannon entropy has a number of desiderata, and that's the reason we actually use. For example, it's an extensive property. And in this case, we can take the log to the base 2. Then, of course, entropy will be measured in bits. If we take to the base E, then it will be measured in terms of Napiers. And we can take the base of the log to the base 10. Then it will be measured in Dossets or logits. Okay. Now, of course, so now let's define, when you are given only one value and we know its probability, then the Shannon entropy tells us that the amount of information that we can gain from the knowledge of that value whose probability is known is really nothing but the minus log of pi. Just like basically now we are saying it's just like knowing the value of a currency. So minus log of pi gives you in numerical way a value of entropy or information associated with the event xi or the value xi, because we know its probability pi. So this is the amount of information associated with any probability named as pi. Now, if you take the weighted average of that, then that becomes log of pi. Note here, I think I mistyped it. It should be minus, not log of pi log. No, I'm sorry. No, it is correct because I've already taken care of minus here. So the Shannon entropy is really nothing but the weighted average of the information associated with the sample values whose information contents are described by the probability. And that information content is given by delta capital II or minus log of pi. Okay, so if we plot, for example, if we plot the Shannon entropy as a function of probabilities, you will find that the Shannon graph will be a convex function of this. So you see here now, when P is equal to 0.5, the Shannon entropy will be maximum. Now it should be so, because if the events are all equally likely, then there is no way for you to discriminate which event is more uncertain and which is less uncertain, because they are equally uncertain. And that's what essentially the graph shows. And then you move away from the maximum value on either side, the Shannon entropy will reduce, and it can become 0 depending upon the probability being 1 or the probability being 0. Enough. Okay. Now, of course, in a continuous form, again, we can also essentially express Shannon entropy exactly in the same way. So where we are now considering not the probabilities, but the probability density function. So small f of x is really nothing but the PDF, or the probability density function of capital X, and log f of x and dx. Now, those of you who have a more mathematical penchant might ready question that if you go from the discrete form to this continuous form, you will have to have an additional term here. And I recognize that because I have purposely not put that, but that additional term will be essentially again log of delta xi. And so basically in the case of continuous entropy, you can say that the Shannon entropy in a continuous form, the way it is expressed is relative to a datum, because that value will define nothing but a datum. So the mathematical concepts as well as the mathematical properties and the values really don't change, because of course in the first course in engineering and statics, we learn about potential energy with respect to a datum. That's the reason we go out and do the survey. So so you don't have to worry about the mathematical finesse here. Okay. So so the second concept now is the principle of maximum entropy. The third concept we have already discussed. So in practice, so what is qualitatively it means? So it can be explained as follows. In practice, it is common that some information is available on the random variable. So that means we would like to choose the distribution of the random variable, which is consistent with this given information that makes sense. So we want to choose that distribution that has the highest entropy. Why highest entropy? It may sound counterintuitive. No, it is not. It is very much intuitive because we do not want to make any assumptions. We don't want to be biased except for satisfying the given information. That's the reason we want to be as unbiased as possible. And this is what is called as the principle of maximum entropy. And this principle of maximum entropy essentially says that we assign the probabilities which will maximize the entropy, subject to, of course, the given constraints of given information. Now, this is consistent with Laplace's principle of insufficient region, which says all outcomes of an experiment should be considered equally likely unless there is a reason to believe otherwise or there is information to the contrary. So that means that entropy defines a kind of measure on the space of all probability distribution, and you choose that distribution which will satisfy the criterion of maximum entropy and the satisfaction of the given information. That's what the principle of maximum entropy is. So which means because you are bringing in your modeling enterprise the given information, that means you are bringing the modeler and the model or the system together. This is how entropy brings the modeler and the science together and the system. So that the fourth concept is, or the fourth element is the concentration theorem. Basically, the concentration theorem says that the spread of lower entropies around the maximum entropy values, basically, so for a given random variable x, whose probability distribution is f of x, the Shannon entropy denoted by h of x basically can be considered or can be bounded by the maximum entropy and the maximum entropy minus delta H. Now, delta H can be defined if we know the sample size, which we know, and then of course from the chi-square distribution, and then of course the upper tail of, or the alpha, which is 5% or 10% or whatever. So H max is given by the principle of maximum entropy or the entropy maximizing. Then it says that for n observations where we have n probabilities, the concentration of these probabilities near the upper bound, which is S max, is given by the concentration theorem. So asymptotically, it says that twice the sample size multiplied by delta H is distributed as x square which is chi-square, with n minus m minus 1 degrees of freedom. Now remember here, small n is the number of class intervals in which you arrange the data. And m is the number of parameters that you have in the distribution. So n minus m minus 1 will be the degree of freedom. And then of course that you can get the values of chi-square distribution at 95% significance level. And so this is how you can get the values of delta H. And so one can compute H max for a given probability distribution function, then the value of chi-square for a given significance level, let's say 5% from chi-square tables can be obtained. Then one computes the value of 2n delta H, which yields the value of delta H. One then determines the range in which 95% of the values will lie and evaluates if the majority of realizations will follow the distribution that we have obtained. So now, having said or having outlined these 4 elements of entropy theory, so how then we apply the theory in real life? So there are 7, 8 steps. One, you define the entropy, then you define the constraint, then you maximize Shannon entropy. For maximizing, then use the method of Lagrange multipliers. So of course, you can use any other method, but this is the easiest one. And then you determine the Lagrange multipliers in terms of the constraints that are specified. Then you determine the probability distribution in terms of constraint. Then you determine the maximum entropy, and that gives you essentially and then you drive the desired result. Before proceeding further, it's very important to note here that perhaps you might have missed. That is that we are driving the probability distribution or driving the system without having any parameters, because the parameters are all explained in terms of the constraints. Constraints are nothing but the codification of the knowledge that we have or the information we have about the system. That means we are characterizing the system in terms of the knowledge that we are codifying, in terms of the information that we are specifying, which means we don't have to worry about estimating the parameters here. So the next question is, how do we specify the constraints? Okay, so first we want to specify the constraints or the information in as simple terms as possible. And we want to specify these constraints which we hope will more or less be preserved in the future. Now, of course, these days, given the climate change, that may not necessarily be the case. But at least, in many systems, for example, mechanical systems, they don't have to worry about the climate change. So we can still preserve. At least that should be our desire. Now, also the constraints should be defined as far as possible in terms of the laws of mathematical physics. For example, mass conservation, momentum conservation, energy conservation, or constitutive laws. I mean, these are the desiderata that you like the constraints to satisfy. So the first, of course, is, the probability distribution must satisfy the total probability theorem. And the second is that we can always specify the constraints in terms of some kind of movements, because the movements are easier to describe. Or we can specify in any other form. They don't necessarily have to be movements. So let's assume the constraints are specified in terms of some G function. And G is subscripted with R. R means we can have as many constraints as we want. So R can vary from 1, 2, 3 to n. So because we are taking constant Cn as the integral of gr of x multiplied by the probability density function multiplied by, of course, d of x, that means we are taking as expected values of the function g of x. So if we do that, and then, of course, if we apply the Lagrange multipliers, then we can immediately construct the Lagrangian function. So the Lagrangian function is really nothing but the way I have expressed here. And then, of course, you apply the Euler-Lagrange calculus of variation for differentiating L with respect to f of x, because our objective is to determine f of x. And so once you do that, then of course, we immediately get in 2 steps. F of x is nothing but the exponential function of lambdas. Now, lambdas here are the Lagrange multipliers. So lambda 0 plus lambda 1, g1 of x. Remember, g1 of x we know because we are specifying it. So the only thing we do not know are unknown Lagrange multipliers, lambda 1, lambda 0, lambda 1, and lambda n. So the next step then is to determine the Lagrange multiplier. So basically, there is a very simple way to determine the Lagrange multiplier. The first thing is you determine the 0th Lagrange multipliers, and it turns out, as I've expressed here, then of course we can determine the constraints the way the next step is. So since lambda 0 will be a function of lambda 1, lambda 2, all the way up to lambda n, so we can take partial derivatives of lambda 0 with respect to different lambdas, and we can show that that will be equal to nothing but the negative of the constraints that we have specified. And so we will have n system of equations, and we can solve for these. We can solve for n Lagrange multipliers. So it's a relatively simple way to do it. Now, of course, if we look at all hydrologic problems, then we can classify them into 3 groups. One, the problems are basically in terms of physics. They are physically based problems. In other words, we need to determine the physical laws, or we need to specify their physical variable. Or some problems are entirely statistical, and some are mixed. So let me give some example. For example, if you are interested in determining a model for runoff or infiltration or soil moisture or movement of pollutants, velocity distribution, hydraulic geometry, channel crossing, these are all physical problems. In other words, we want to determine them hopefully using the laws of physics. Second, statistical, where we are only dealing with bunch of numbers. For example, we are doing frequency analysis, whether we do as engineers frequency analysis, or you can give the same numbers to a statistician who does not know anything about what these numbers really are saying. He can do just as good a job, perhaps even better, being a statistician. So these are called statistical problems. And then, of course, there are a number of mixed problems where we partly use statistics and partly use the physical. And so I will give you just basically, okay, so for the first, I'll illustrate here just the first type of problems, the physical problem. So in the case of physical problems, obviously we have to use the entropy theory, but we also need to specify some kind of a flux law. Flux means the relation between flux and concentration. So remember, by definition, concentration is like a measure of, as they say, the measure of concentration. So let me give an example, perhaps that might clarify. Take the case of open channel flow. So the concentration is really nothing but the height, the depth of water. This is how the water is concentrated. And you can measure the concentration simply by measuring the depth of flow. Whereas the flux is really nothing but the volumetric rate of flow per unit area per unit time. So in this case, flux is really has a connotation of velocity. But you can also specify flux for the energy, or you can specify momentum flux also, as we do in open channel hydraulics at the undergraduate level. So it can be any quantity. Basically, flux is really nothing but a quantity, either the volumetric rate or the concentration rate on a per unit time basis. That's what you call flux. Okay. So So we need to first determine the flux. So the flux, as I said, we have to specify the relation between flux and concentration. Now, or here the relation, as I said, flux normally on a per unit basis, but it can also be defined on a per unit space basis. For example, in the case of in the case of soil moisture, you define soil moisture in the space. So if X is a space average, then it can be considered as a random variable. For example, spaced average infiltration capacity rate can be considered as a random variable, or spaced average soil moisture can be considered as a random variable. And or in many cases, you take the time averaged flux as a random variable. So it all depends actually what the variable is that we are trying to determine the distribution for, or the type of system that we have for. For example, in case of velocity, we take the time average velocity at a given cross section as a random variable. Okay. So there are, there are different ways in which the flux concentration has been defined. Look at the second expression. Second expression says the cumulative probability distribution function of, let's say, spatially averaged velocity can be defined as the concentration divided by the maximum concentration. Because remember, the left side has to be between 0 and 1. So the right side has to be normalized. But a more general expression can be the first expression, like f of x can be defined also actually as alpha 0 plus alpha 1 y over d alpha t, where x here denotes is essentially the variable that we are interested in. Okay. So let's take a now, of course, in hydrology, entropy theory has been applied to hydrologic forecasting, precipitation time series analysis, rating curves, morphological analysis, velocity distributions, water distribution networks, water resources assessment, water quality, wastewater treatment risk, and many other areas. I personally have applied to almost all of these areas and many more. And so entropy makes, okay, so now let's, in the context of those three classes of problems that I specified before. So for example, if we only do maximization without worry about the flux law, for example, in frequency analysis, parameter estimation, network evaluation and design, spatial analysis, geomorphologic analysis, grain size distribution, here really we are not using any engineering per se, except the data relates to engineering problem. So this is strictly a data crunching issue, or these problems are really nothing but statistical problem. Now, of course, we can couple with the theory of minimum energy dissipation rates, for example, in the case of hydraulic geometry, then it represents a mixed type of problem. Now, if we couple that with a flux type relation, then of course, the problems are related to like infiltration, soil moisture movement, rainfall runoff relation, rating curve, flow duration curve, hydraulic geometry, erosion and sediment transport, debris flow, longitudinal river profile, velocity distribution, sediment concentration. All these problems basically fall in the first group, the physical problem. So again, exactly, it is the same methodology as we discussed in the general case. In the same way, we apply the entropy theory in hydrology. For example, we define the entropy, Shannon entropy, Salas entropy, or any other entropy like Berg entropy in the frequency domain, specify the constraint. Then we formulate the fundamental hypothesis. If the problem is physical or hydraulic, maximize Shannon entropy. If we choose the Shannon entropy for application, then we specify Lagrange multipliers, determine the Lagrange multiplier, then we determine entropy distribution in terms of constraint, maximize Shannon entropy, and then we derive the final result. So let me illustrate this methodology for the case of infiltration. So for example, the infiltration is really defined as the rate of entropy of water in the soil surface. So in infiltration, we define potential infiltration rate, actual infiltration rate, steady infiltration rate, cumulative infiltration rate, maximum soil moisture retention, and soil porosity. I think we are all familiar with these terms. So let's assume that infiltration denoted as capital I is a random variable. Now in this case, remember, because we are determining infiltration as a function of time at the soil surface. So we are assuming, because the infiltration vary from one point on the surface to another point. So in order for infiltration to be regarded as a random variable, we assume that the spatially average infiltration can be considered as a random variable, and which can be justified because at different points on the surface of a watershed, infiltration will be different because the soil characteristics are different, the landscape is different, the vegetation is different, and so on. So it is reasonable to assume that spatially averaged infiltration can be considered as a random variable. So now we can define the movement constraints as we did before. Now, of course, once we do that, then as I said before, the entropy based in the probability distribution of especially average infiltration I will be really nothing but, which we have actually expressed before. Now, since let's assume that we don't know anything about infiltration, which means the number of constants is 0. We don't know anything. Now, knowing that, I will derive for you, but using the entropy theory, I personally have derived all these equations: Horton equation, Kashtakoff equation, generalized Horton Kashtakoff equation, Smith-Parlange equation, Philip-Tutram equation, Green-Empt equation, Overton equation, Holton equation, and of course, one of my students, you and I derived it, called Singh generalized infiltration equation. All these equations actually, I have derived it using infiltration theory. So we'll just illustrate the case of Horton equation. So let's assume in the case of Horton equation, we don't know anything about infiltration. We only know that we do not have any understanding of infiltration. So that means there are no constraints. And let's define small I, which is the axis infiltration. So capital J is the axis cumulative infiltration, and S is the maximum excess soil moisture. X is the infiltration above steady state infiltration, because steady state is just like a datum, it's a constant value. But really, you don't have to do it. I just did it for simplicity, but you don't have to take the excess infiltration. So that means cumulative distribution of I, this is a flux law. We can define as 1 minus capital J divided by S. So capital J is the axis cumulative infiltration, and capital S is the maximum excess soil moisture retention, which is really nothing but the maximum soil moisture minus whatever the soil moisture is already there in the soil. So there is no constraint. So the only constraint is total probability constraint. This is not really a constraint because the total probability has to be satisfied. So the probability distribution actually will be nothing but in one line you can find that f of capital I will be nothing but 1 over I0 minus IC. So what is I0? I0 is the initial axis infiltration, and or axis infiltration capital IC is nothing but the initial or the steady state infiltration. And if you do a little bit of algebra, apply the flux law, you will immediately find the Horton equation just in 2 lines. Now, but what is important is here the entropy theory tells us this Horton parameter K is really nothing but the ratio of the maximum soil moisture retention capacity divided by the difference between initial infiltration minus the steady infiltration, which means the capital K is nothing but the time of travel. This is the average time of travel the water takes from the surface up to the time the infiltration becomes constant or it reaches the value of steady state. And we applied this, remember, without any fitting whatsoever. We knew what the initial infiltration is, which you can determine, which obviously you have to know because this is the antecedent state of the soil moisture. And then you have to know, because for this soil, which is Robertsdale soil, Robertsdale loamy sand, so we know what the steady state infiltration will be, which is really nothing but some fraction of the saturated hydraulic conductivity that we know if we know the soil. And look at here. And we actually, you find the Shannon entropy without doing any parameter fitting does an excellent job. And then we also try to estimate the infiltration parameters F0 and I0 and IC and K using least squares method. And the least square method is slightly better, obviously, because we are trying to fit. And this is for another soil sample. Well, look at, yeah, another soil sample, but without, so once we said, okay, because the maximum soil moisture retention capacity is not really exactly known, because this is really nothing but equal to porosity. So porosity, so we said, okay, let's take this as approximately equal to 0.8. The reason we took 0.8 is because the soil always has some obstructions like earthworms, or it has some roots or some debris. So that means the porosity is not exactly equal to the porosity that you determine in the lab by sieve analysis. So we took arbitrarily, we took 0.8, there was no fitting here. And we find that the entropy theory almost fits the curve. And this we did for a number of soils. And we find exactly the same thing. So what I'm saying here is that the entropy theory allows you to take into account the knowledge that you have about the soil, and you can determine the infiltration or the Horton equation. But the important thing is that now you can interpret the Horton parameter in terms of physical, physical significance. Now it tells us, in fact, when I was teaching hydrology many years ago at the undergraduate level, I knew what K was, but I did not really spend as much time thinking about the physical significance. But when I started many years ago applying entropy theory, then it occurred to me that basically the value of K, which is Horton parameter, is nothing but the average travel time. In other words, it's a function of the mobility of the soil. In other words, it's just like traveling by car from one place to the other. You can determine how much average time it will take. This is what Google does, because Google obviously gives you an exact time, because Google is able to map the distance between the 2 points, and it's able to map the average speed, and assuming the average speed is able to map what the obstructions will be if there is a traffic jam or anything, then based on which then you determine the average time of travel, which turns out to be always perfect. So let me now conclude. I think I have taken a little more time. That basically there are two fundamental issues when you apply the entropy theory. One, you have to hypothesize a flux concentration relation if you are dealing with a physical problem, and you have to specify the constraints, hopefully based on the laws of physics. Then the use of entropy leads to explicit expressions of the flux in terms of the concentration, as I did. For example, in case of infiltration, our flux is the infiltration rate because it tells you the volume of water entering the soil on a per unit area basis. And then, of course, the concentration is the cumulative infiltration. That is the concentration. And of course, the parameters so derived seem to have physical meaning. So entropy theory actually provides a probabilistic description and makes a statement on the uncertainty. And this has important implications for sampling and model reliability. In case of Horton equation, not only you get Horton equation, but you can also specify the uncertainty associated with the Horton equation, and you can specify the probability distribution of Horton estimated infiltration value. Each value can be associated with a probability because you have a probability distribution. So basically it tells you three things. One, it gives you a physical interpretation of Horton parameter. Two, it also gives you the probability distribution of Horton parameter. Okay, I'm talking. And then of course it gives you the uncertainty associated with Horton estimated infiltration. So with that, let me conclude my presentation. And as I said before, and let me reiterate, I will be happy to answer any questions that you might have. So Dr. Prasad, can you hear me? Can you hear me?
Yes, please.
Okay.
Just. Hello. Hello.
Yes. Yeah, go ahead.
Thank you for your nice presentation. And many of both from India and internationally they joined this webinar. Now we shall, I will invite some of the participants to participate in this question and answer session. And I just start with our Dean herself. She just okay, before the thing, I'm just requesting some of the attendees to interact with the professor. Just a moment.
Okay.
Mr. Jajaria. Hello.
Hello.
Yes, I can.
Mr.
Yeah, go ahead. I
Jajaria.
can.
Good evening, sir. This is Zachary from Chhattisgarh.
Yes, Jaria, how are you?
I'm fine, sir.
Okay.
Sir, as you mentioned that we can average infiltration spatial variation.
Yes.
There is the depth-wise variation is also there. How we can deal that, sir?
No, okay. So, remember, infiltration is defined as the rate of water entry into the soil. So you are only defining the
Yes.
infiltration at the surface, not if you want to define the depth below, then you have to estimate the soil moisture, which you can also do likewise.
Yes.
So the reason you take the average, especially average infiltration, is because, as I said, infiltration at each point is different. In order to determine a representative infiltration value, you have to take an average infiltration value. So especially average infiltration can be considered as a random variable. And then of course you can apply the entropy theory. So the value that you specify for infiltration is a point value, but the connotation is that this point value is especially averaged because you are not specifying infiltration at every point, but rather you are specifying especially averaged infiltration. Now the especially averaged value represents the value for the space that you specify. For example, you can specify the space as a plot. You can specify space as if having a particular dimension like 1 meter by 1 meter, 10 meter by 10 meter. If it's a small water set, what you normally do, you specify just one value for a small water set, but you don't have to. You can divide the water set into different units, hopefully spatially uniform, and then you specify infiltration for each unit.
Yes. Sir, one more question I have.
You can have as many questions as you want. Why one more?
Thank
Ask
you
more.
very much, sir. As sir, in Central India, that we have a scope for that karst aquifer study. So
Yes.
can we apply this entropy, that study for Proterozoic karst aquifer modeling? If
Yeah,
yes,
you
sir,
can-
which
yeah,
entropy is most useful?
Yeah.
Because-
You can
yes.
you can apply entropy theory to karst aquifers. Yes, actually there are certain papers that people have applied entropy to groundwater modeling.
Yes.
And you may want to look at, I personally applied entropy theory for groundwater modeling only in the case of phreatic aquifers. But your karst aquifers are a little more complicated.
Yes,
But
sir.
you want to take a look at, there was a paper published in Water Resource Research some years ago, and they applied entropy theory for a little more complicated groundwater modeling. So I think you can actually apply it to any problem.
Yes, sir. Okay. Thank you very much. Sir,
You're welcome.
which entropy will be most useful for hard rock aquifer, like limestone or karst aquifer is treated as a
Oh.
hard aquifer?
Okay,
Which
no,
will be
I
more
think that,
suitable?
yeah, I think apply the Shannon entropy, because Shannon entropy, the mathematics is much easier to deal with. In the case of Salaf's entropy, Rennie entropy, and Kapoor entropy, the mathematics becomes a little more complicated. And so just apply Shannon entropy. They will provide pretty much the same result.
Yes. Thank you very much.
Thanks, Satish. Now I request Dr. Dharma Hagare from Western Sydney University. Hello.
Okay.
Hagare.
Hello. Hello, Professor Singh. Can you hear me?
Yes, I can hear you quite well.
Yeah, I'm Dharma Hagare. I'm from Western Sydney University. I work with Basant Maheshwari.
Please introduce yourself, please.
Yeah.
Dharma.
Yeah. I'm from Western Sydney University. I work with Basant Maheshwari.
Yes, yeah, Basant is a family friend, yes.
Yeah. I've read some of your books, some of your papers, and I heard a lot about you, and it was great to hear your lecture today. It was really interesting.
Thank you.
But I must admit, I haven't really used the entropy theory in any of my modeling. But it was really interesting to hear, how the entropy theory can be used in hydrologic modeling. Now, I think again, I think my question may be a bit ignorant of me, I suppose. What you're saying here is, the entropy theory is basically latching on the physical theory to provide a solution, I suppose. Am I right?
No.
No.
It,
Okay.
it is the other way around.
Okay.
Entropy theory is an independent theory. It is not getting latched onto a physical theory. All I was saying was you can actually bring into entropy theory the laws of physics. For example, if you want to derive the distribution of velocity in open channels, for example, then you can invoke the principle or law of conservation of mass, the law of conservation of momentum, and the law of conservation of energy, which will be nothing but the constraints that the velocity distribution must satisfy. And then you can apply the entropy theory for deriving the probability distribution of velocity as well as the distribution of velocity as a function of space coordinate, just like we do. For example, in case of open channel flow, the velocity distribution is expressed either as a power law or as an exponential law.
Okay.
So both you can derive. So depending upon what you really want to do, because velocity distribution derivation is a physical problem, so you would like to apply the laws of physics as in the form of constraint, and then you apply entropy. So you can derive, you can accomplish actually several things, as I said before. First, you can derive the velocity distribution as a function of space coordinates in 1 dimension, 2 dimension, 3 dimensions. Second, you can also, and this is the only way that you can actually drive the velocity distribution unless you apply in a using a very complicated mathematics, the Navier-Stokes equation. Second, you can also get the probability distribution associated with the average velocity, which you cannot get if you only apply the physical laws, for example, Navier-Stokes equation. Third, you can also interpret the parameters appearing in the velocity distribution because you start out with a constraint. And I personally have done this. For example, if you use the, for example, the exponential law for velocity distribution. So what do you have? You have two parameters appearing in the exponential distribution. One parameter is the thickness of the viscous sublayer, right? And so the thickness of viscous sublayer, there is no way, I mean, this has always been has been very elusive, but the entropy theory actually allows us to explicitly determine an expression for the thickness of the viscous sublayer depending upon the roughness element, the density of the fluid, which in this case is water, or if it is sediment laden water, and then of course the the flow laws. So you can actually specify how high the viscous sublayer will be, and so this is how it gives you a lot more than what you will be able to get otherwise. So what people normally do is they empirically estimate these parameters.
So the other thing is, it basically uses the probability theory. So when you use the probability theory, you need a lot of data, I suppose. So don't you think entropy theory is a bit site specific?
No, it has nothing to do with site. I didn't say anything about a particular site. I'm saying as long as you are able to specify the constraints. The constraints are not related to site. Constraints are related to the particular characteristics of the system that you are trying to model. And you are not using a whole lot of data. You are specifying. So in other words, the entropy theory is the only way by which you are able to integrate your understanding of the system with the information theoretic framework.
Okay.
So, if you, for example, let's assume that you only want to deal with the probability theory. If you deal with the probability theory, how would you determine, let's say, the velocity distribution or the infiltration function or the soil moisture profile or the sediment transfer? There is no way you can determine it.
Yeah.
The probability theory will only give you the probabilities. Whereas here you are able to specify the probabilities. The only thing that it will require you to do is to specify the constraints, which makes sense because you ought to know the constraint.
Okay, fantastic. Okay, thanks so much. Thank you.
You're welcome.
Now I request Shakila.
Yes. Hello, sir.
Yes.
Hello, sir. I'm Shakila Javed, working as a lecturer in Muscat. Can you hear me, sir?
Yeah, I can hear you quite well, Shakila. It's good to hear your voice.
Your sir, lecture was very informative. Actually, sir, I have one question. Like, can we use, sir, this theory for coastal modeling, coastal aquifer modeling? For
Yes,
limited data, we don't have much. We have very limited data. Can we use this theory for that?
Yes, you don't really need too much of data. As I said, you can use your knowledge of the coastal aquifer that you are trying to model. And based on that knowledge, you can do the modeling.
Okay, sir. Thank you, sir. Thank you, sir. Means we
You're
can,
welcome.
right, sir? Thank you.
Yes. Yeah.
That was only my, sir. That was only my question.
Okay.
Hello. Dr. Sharad Jain. Hello. Dr. Jain? Dr. Jain, your audio is
Yeah.
good.
Hey, Sharad.
Hello, namaskar, sir.
Looks like you are at home.
Yeah, I am at home. It is, I think, 6:30 in the evening now. So I just came home to listen to your
Yeah,
lecture.
it is 8 o'clock here in the morning in the college station.
Yeah, it started at 6:30 of your time. It was quite early. So, as expected, it was very useful lecture, and whenever we hear from you, we always learn something new.
I'm not so sure. You are always too generous.
No. And next semester, I think I'll be teaching a course on hydrology. So probably I'll try to introduce this concept also, and I'll interact with you when you happen to come here or maybe some other time.
Okay, yes. I think this is really something I very strongly feel. There are certain theories that every engineering student must learn. Entropy theory is one of those theories. And the other theory, which has nothing to do with probability, is the kinematic wave theory. Every student must learn kinematic wave theory. I mean, the kinematic wave theory you can apply all across the board in hydrology. And this is something every undergraduate student must have an understanding. And in many ways, the kinematic wave theory is also like entropy theory, because basically one uses the law of conservation of mass and the flux law, which is really nothing but people express that in many different ways. For example, they simply say it's a simply form of momentum equation, but really that is nothing but the flux concentration law. And so anyway, I think I'm glad that
Just a very small question.
Yeah?
Just a small question.
Yes.
When you talked about this cross entropy, then you
Yes.
mentioned that there were two distributions. And if the distance between them is minimum,
Yes.
then more uncertainty.
Yes.
Does it not look counterintuitive? I think if the distance is less, then
Yeah, it looks, but actually it is not. Okay, let's put it this way. Let's assume that you want to be as unbiased or as objective as possible, right? So which means that you want to be as uncertain about an object, about a human being, or about a system as much as possible. So in order to become most uncertain about that person or reduce your bias, what you have to do, you have to maximize the uncertainty.
okay.
Which means so the prior distribution, let's assume, is uniform. So that means you want to be as close to the uniform distribution as possible, subject to the satisfaction of the constraint that you are specifying. So you are saying that you want to make sure that you satisfy the constraint that you have, but beyond that, you don't want to make any assumption whatsoever. Suppose, for example, you have just stepped down as a director. So when you were director and you interviewed a lot of people, and as a director, you selected a lot of scientists, right? So what did you do? You based your judgment strictly on their performance, isn't it? So which means you only took into consideration two things: their performance in the written exam or oral exam, as well as their records. Beyond that, you did not make any assumptions at all, which means you try to stay as far away from those candidates as you possibly could.
Okay.
This is exactly what you are doing in case of cross entropy.
Good. Yeah, thank you.
Now, next attendee, Sahana from IIT Bombay. Sahana, can you hear me?
Yes, sir.
Please
Everyone.
Please introduce yourself.
Yeah, very good morning, sir. Good morning, sir. Hello.
Yeah, good morning. It's good to hear your voice, Sahana. Can you hear me?
The very presentation and unique. Yeah, I can hear you.
Okay.
Hello? Yeah, I can hear you.
Yeah. Okay, Sana, go ahead.
Yeah, so yeah, I'm working on a multivariate drought assessment. So I wanted to apply this entropy theory for drought vulnerability assessment.
Okay.
So I have certain drought vulnerability indicators where I would want to, find the indicator weights to calculate my drought vulnerability.
Okay.
So is Shannon entropy appropriate to find the weightages that way?
I think so.
Hello?
Yeah, I think you can.
Yes.
You can actually apply entropy in other ways also. For example, you are doing multivariate modeling, right?
Yeah.
Okay, so in multivariate modeling for individual variables, how are you determining the probability distributions?
So I'm using copula theory to combine my two
No, no.
variables.
Yes, yeah,
Find
you are
out-
using, yeah, but in order to use copula theory, you have to determine the marginal distributions. You have to specify the marginal distributions, right?
Yes. Yeah.
How are you determining those?
So for each of my drought variables, I am fitting a marginal distribution based on.
That's the point I'm trying to make for you. Why do you have to fit? Why don't you apply the entropy theory to derive the univariate distribution? And then you apply the copula. In other words, so you can combine the entropy theory with the copula theory. And then, of course, you proceed further. So that way you avoid all this